Isaac Newton and the apple. In a previous assignment, physics students were asked to tell what they knew of the famous story of Isaac Newton and the apple. Here are some replies. Isaac Newton was sitting under an apple tree and an apple fell on him and he thought of the idea of gravity. Isaac Newton was sleeping under an apple tree and was awoken when he got hit on the head by an apple. He then wondered what exactly caused the apple to fall, the force that drove it. Then he did math. What I know is that Newton was sitting under a tree somewhere as suddenly an apple fell on his head, and that's how he discovered gravity. I don't know how that gave him the idea, but that's what my old math teacher used to tell us. I've heard was that he was sitting under a tree, probably doing some sort of math, inventing something new, and an apple falls on his head. Then he thought, why does it fall? Why doesn't it float or fly across the field or wherever he was? I remember the story going as Newton was sitting under a tree and saw an apple fall and was like, why? Then he was like, oh yeah, must be gravity. I don't know anything about the story of the physicist and a piece of fruit. I have never heard of the story before. To be honest, I've never heard of that saying before, so I don't have any knowledge of what it means. Okay, it's not surprising that there are some students who've never heard the story at all. I know that it's very common that people have this comical idea of an apple falls, hits him in the head, and he's, gravity. It's all related to the truth somehow. It is a real story. Newton did not talk about getting hit in the head by an apple, but he did talk about an apple falling and the thoughts that it led him to. He was fond of telling this story as an older person. So let's tell that story. Before telling the beginning of the story, we'll tell a little bit from the end of Newton's life. He passed away in 1727. By that time, he was already a world-famous figure, someone who was known to have changed the way we look at things, helped us move toward a more modern world of understanding and rationality. English poet Alexander Pope wrote this: "Nature and nature's laws lay hid in night. God said, 'Let Newton be,' and all was light." Alexander Pope hoped that would be included on Newton's monument in Westminster Abbey. It's not there, but there are other words in praise of his accomplishments. But let's go back. Where did this get started? Well, let's tell the story. Here's a little story about a boy and his apple. The boy's grandfather, Robert Newton, was a successful sheep farmer who had purchased a farm called Woolsthorpe Manor in Lincolnshire, England. Robert's son Isaac inherited the farm, married Hannah Icecoff, and unfortunately died 6 months later. About 2 months after that, early in the morning on December the 25th, 1642, the same year in which Galileo had died in Italy, Isaac and Hannah Newton's son was born at Woolsthorpe, in this house, in the second-story room on the left. The baby was named after his father. Baby Isaac was premature and tiny, and there was doubt he would survive. But of course he did, or we would not have a story here to tell. Hannah Newton assumed her son Isaac would be a farmer, like his father and grandfather. But an uncle noticed the boy's intelligence, and he was sent to this school in nearby Grantham, where he studied from the age of 12 until 17. Classes were held in this building. While at school, Isaac was at first an unremarkable student. He was very quiet and kept mostly to himself. There is a story that he was repeatedly picked on by a bully until one day he decided he had had enough and he fought back, winning a fight. Still fuming with a sense of "I'll show you," Isaac decided to fight back in another way by working hard and becoming the top student in his class. He won that fight too. At some point during his stay at Grantham, he etched his name in a stone windowsill, where it remains to this day. After Grantham, a move back to the family farm did not last long. Isaac disliked farming intensely, so he jumped at the chance to study at Cambridge University, which does bear a certain resemblance to Hogwarts, although perhaps it is really the other way around. At Cambridge, Newton lived in campus housing with other students. His room is on the second floor in this photo. The windows are behind the tree branch in the upper left. In Newton's time, the apple tree you see here was not there. Not yet. Studies at Cambridge focused on the classics, works by Greek and Latin scholars such as Plato and Aristotle, but Newton also became familiar with newer work by Galileo, Kepler, Descartes, and others. He distinguished himself as a mathematician, and at 23 had just earned his bachelor's degree and had begun work on his master's when the Great Plague of London. In 1665, a disease quickly spread through the city, killing people by the thousands. Schools and businesses closed, and people sought shelter in their own homes. This was a new and widespread outbreak of the plague, a sadly familiar occurrence in Europe in those days. No one knew the cause of such illnesses at the time, but people knew enough to avoid crowds and to isolate themselves for self-protection. With Cambridge closed, Isaac Newton headed home to Woolsthorpe Manor. And then, well, there was nothing much to do for a while. Isaac Newton had been thinking about orbits. Back in Cambridge, this had been a hot topic among the few students who knew of the radical ideas of Galileo and Kepler. This was a mystery the greatest minds could not solve. How could a system function where moons orbit planets and planets follow elliptical orbits around the sun? One lazy afternoon, according to the story he told many years later, Isaac was sitting alone in the garden, near this apple tree. Yes, this tree and the house and the school are all still there. It's only been 350 years or so. In England, past and present have a way of blending. Anyway, on with the story. Perhaps this was one of those days when the moon is visible in the afternoon sky, as you've probably seen from time to time. Newton did not mention that detail, but it helps to paint the picture. Who knows? It may even have been true. As Newton sat, contemplating, by chance an apple fell to the ground. Newton saw it fall, and it got him to thinking about why it fell, and in particular, why it fell straight down. And then he got it. He knew how everything worked. The end. Oh, you want to know what he was thinking? Okay. Newton saw the connection between the apple, the moon, the earth, and the rest of the universe. And he saw why the question of orbits had proved so difficult. Orbiting moons and falling apples are objects in motion. The problem was nobody understood motion in general. Once you understand motion in general, orbits are easy. That problem was no one understood how to describe motion correctly using math, because that required ideas that didn't exist yet. No one really understood motion, and no one knew the math to describe it for a simple reason. Before that apple fell, the reason was that no one had ever thought the right thoughts. After the apple fell, the reason was simpler still. Isaac Newton hadn't told anyone yet. On the Shoulders of Giants. 10 years later, in a letter to fellow scientist Robert Hooke, Newton wrote, "If I have seen further, it is by standing on the shoulders of giants." Galileo was likely one of those Newton was referring to. Here are 3 ideas that Galileo wrote about, and with which Newton was no doubt familiar. Number 1, Galileo's law of falling objects. As Galileo discovered, and as all physics students learned earlier in their first year, all objects fall at the same constant acceleration, g, 9.8 meters per second squared. The weight of the object, the material from which it is made, the object shape, none of that matters if we can ignore air resistance. In a vacuum, without the effects of air resistance to hide the true nature of falling motion, all objects behave the same. Aristotle had taught that different objects had different natures. Galileo's law is a universal mathematical law that everything on Earth follows. He showed that, at least in the case of falling motion, everything has the same nature. What applies to one object applies to all. Number 2, Galileo's story of a sailing ship. Before we get to the story, a question. Is this ship moving? Of course, I'm asking you to pretend that it's a real ship for the moment. How could you tell if it was moving? Yes, I know it's not moving on the screen. It's not moving compared to the text, but in real life, how could you tell if the ship is moving? I mean, what if the ship is sailing to the right at 10 miles per hour and you are watching it from a window on another ship that is also sailing to the right at 10 miles per hour? Would things look any different than if both ships were at rest? You may be thinking, if the ship were moving, the ball would land in a different place. Not true. It wouldn't, because the ball would be moving with the ship. To someone on the ship, there is no way they can tell the difference between moving and not moving, except by comparison with something external, like an island, a dock, or the surface of the ocean. To verify that reality does work the way he thought it did, Galileo actually did this experiment. The ball falls straight down from the point of view of someone on the ship, whether the ship is moving or not, compared to the Earth. To argue against the idea that the Earth orbits the Sun, Galileo's critics made a very common sense argument. If the Earth is moving, why don't we feel it? Simple calculation shows that if the Earth really is rotating once a day, any point on the equator must be moving at about 1,000 miles per hour just to keep up. The speed of the Earth in orbit is greater still. Surely we would notice such motion, the critics said. Galileo replied that no, we do not notice motion, except by comparison to some external reference. A sailor below deck on a sailing ship cannot tell the difference between the ship at rest and the ship moving smoothly at a constant speed across a calm sea. If you watch from a dock that is stationary with respect to the ship on the left, you will see the ship on the right as moving, and you will see the dropped ball on that ship travel in a curved path, a parabola. But to the sailors in each of these ships, the paths of the falling balls look just the same, straight down. Both sailors are at rest compared to their ships. You are at rest compared to the Earth, so you cannot feel its motion. Number 3, Galileo's concept of inertia. Two of Galileo's most famous experiments studied the swing of the pendulum and the rolling of a ball on an incline. They have something interesting in common. If you release this pendulum bob from rest here, how far will it rise on the opposite side of the swing, ignoring friction and air resistance? The bob will rise to the same height on the other side. Okay. If you release this ball from rest here on this incline, how far will it rise on the opposite side of the rim, ignoring friction and air resistance? The ball will again rise to the same height on the other side. Okay, very well, Galileo thought, but Here's where the touch of genius shows. What if there were no opposite side? The ball would go on forever, ignoring friction and air resistance. And here's the big point. Once it gets moving, the ball does not need to keep being pushed to keep moving. It does that all on its own. We call that tendency to keep on keeping on inertia. The heavier the object, the stronger the inertia. Aristotle said that without a constant push, earthly objects would come to rest. Guess what? He was wrong. Unless pushed by frictional forces, a moving object will keep on going forever because of its own inertia. Summing up Galileo's contributions. Number one, nature's laws are universal and mathematical. Number two, velocity is relative. You cannot feel constant velocity. And number three, objects have inertia. No force is needed to keep something moving once it's already going. Okay, back to Woolsthorpe. Pretend you are Newton. What did he see that no one else had seen? Let's take it one bite at a time. First of all, the apple fell straight down, as if something pulled it that way. What's straight down? The center of the earth. The apple got pulled toward the center of the earth. The earth pulled the apple. Would the same thing happen if the tree were taller? Of course. Is there any reason to suppose there is some magic height that is too far to fall from? Of course not. Think of raindrops. The earth pulls things towards its center, no matter from what height. Number three, laws, remember, are universal. There's nothing special about apples, or the earth for that matter. If the earth pulls the apple, then it must be that everything pulls everything else. Earth pulls apple, apple pulls earth pulls moon, moon pulls earth. Everything attracts everything else. Otherwise, it's not universal. Let's call that attraction gravity. Why didn't the apple fall sooner? Well, there was a stem holding it up. It only fell when the stem broke. Forces must be able to cancel each other out. If in balance, the apple only fell when the forces became unbalanced. What did that unbalanced force of gravity do to the apple? It's Galileo's law. The apple accelerated toward the ground. Laws are universal. If the force of gravity accelerates objects, then all forces must be able to accelerate objects. That's what forces do, cause acceleration. Well, what is acceleration anyway? It's the rate at which velocity is changing. Logically, the stronger the force, the greater the rate of change. Forces do not cause motion. Sorry, Aristotle. You don't need a force to keep moving. Remember inertia? Forces cause changes in motion. A stronger force makes the change happen faster. Force is proportional to the rate of change of velocity, to the acceleration, not the speed. If nature follows mathematical patterns and the forces between objects affect the rates of change in motion, then there must be some mathematical way to relate forces and rates of change and other quantities. Well, this step took Newton a while to work out, but in principle, he knew there ought to be a way to do such calculations. Let's call that way calculus. But let's go back to the start. What does this have to do with orbits? Well, if the Earth pulls on the apple, it must pull on the moon, like swinging a weight at the end of a rope. If the Earth pulls the apple down and the Earth pulls the moon too, then why doesn't the moon fall? There's no stem to hold it up. Let's let that one simmer for a moment. Give you a chance to think about it. Why doesn't the moon fall? It's a trick question. The moon does fall. It's not straight down. If the Earth pulls the moon down, why doesn't the moon fall? Well, laws are universal. If the unsupported apple falls, so does the unsupported moon. The moon is a falling object, just like the apple. It does fall. But what you really want to know is, if the moon is falling, why doesn't it hit us? Because the moon is already moving sideways, and its inertia keeps it going sideways fast enough that it always misses. Also, forces do not cause motion, they cause changes in motion, acceleration. Gravity changes the moon's path from straight to a curve. If the moon's speed is just right, the curve will be a circle around the center of the Earth. If the speed is slightly off, which it is, the path will be not a perfect circle, but an ellipse instead. The moon in its orbit and the apple falling to the ground are both doing the same thing, falling. That's the big point. The apple and the moon are both objects being pulled to the center of the Earth. The moon moves sideways as it falls. The apple doesn't. But they're both doing the same thing, freely falling while being pulled toward the center. We call this a centripetal force on the moon. The moon's inertia would carry it off in a straight line, except the Earth's gravity force constantly pulls it toward the center of the Earth. The centripetal pull changes the moon's velocity by bending its direction into a closed loop, an orbit. The moon is falling in a circle. Now, this idea can be difficult to get, to really be convincing, to really get. So when Newton got around to putting all of this in a book, he came up with this picture, this thought experiment, Newton's mountain. This is an actual diagram from the book. Imagine a cannon on a mountain. In this diagram, the cannon is right at the top there where the letter V is. And the idea is if you fired a cannonball to the right, if it had a little bit of speed, it would land there at point D. With more speed, it would land at point E. Even more, it would land a quarter of the way around the Earth at point F, or maybe even halfway around the Earth at point G. The faster and faster the cannonball goes, the further it gets. Essentially, it's firing the cannonball over the horizon, and the cannonball's falling just as fast as it can, but the ground is curving out from under it. To help explain this better, here's a short excerpt from an episode of the PBS documentary series, Nova.
To show how gravity works on Earth and in the skies, Newton designed a thought experiment. He imagined firing a cannon from the top of an extremely tall mountain. From his first law of motion, he knew the cannonball would travel in a straight line at a constant speed forever. But gravity pulls the ball downward. If its speed is low, the cannonball hits the Earth near the mountain. The higher the speed, the farther away the ball lands.
If you throw it faster, it comes farther away. Even faster, farther away. Even faster, it may go 1,000 miles. even farther. It may actually go almost halfway around the Earth, and there hit the Earth.
Newton imagined that if its speed were high enough, the cannonball would travel all the way around the Earth and settle into orbit.
The orbit of the cannonball around the Earth was a balancing act between the cannonball's tendency to fly off in a straight line and its being yanked back towards the center of the Earth continuously by the force of gravity.
Newton's breakthrough was to see that the moon's orbit around the Earth and a cannonball's motion on Earth were governed by the same law of gravity.
That is a beautiful way of persuading you, me, and probably his colleagues that cannonballs falling to the Earth and the moon falling to the Earth is one and the same law of physics, gravity. The moment that he realized that, almost everything else follows from that.
Newton reasoned that if gravity governed motion on the Earth and the moon, why not on Jupiter and its moons, which he had seen with his reflecting telescope? Why not the entire solar system? In a bold leap, Newton proclaimed that this invisible force operates everywhere in the universe. Newton called it the universal law of gravitation, and he wrote it in one simple mathematical equation.
It's so important because it really tells us how nature operates in a fundamentally new way. Newton is saying the same thing that is going on in the heavens is going on Earth, and vice versa. It gives us a guidebook to answering the age-old question of what causes the rise and fall of the tides. It gives us answers to the orbits of the planets and their positions. It's a tremendous act of intellectual triumph, one of the great keystone, cornerstone pieces of our intellectual heritage.
It was a total revolution. The universal law of gravity was a complete revolution the way that we think about the world, the solar system, therefore the universe, whatever the size of the universe was in those days, and therefore the way we think about ourselves.
The Principia showed a promise that gravity by itself could account for virtually all the motions we know of in our planetary system. And the rest of science to this day has built off of that foundation.
The laws of nature are universal laws. The apple falls to the earth, the moon falls around the earth. The earth and all the other planets fall around the sun. Orbits are simply falling. It's all the same thing, the same pattern, the same universe, the same rules at heart. As an object in a circular orbit moves, it needs to go sideways because of its inertia just fast enough so that as it falls because of the Earth's gravity, the ground below curves away just as quickly as the object falls. That way, it never loses height. Near the surface of the Earth, the speed needed to do that is very fast, about 5 miles per second, or almost 8,000 meters a second. Launching a satellite into orbit requires getting it above the atmosphere and also getting it moving sideways fast enough that when the rocket engine goes off, the satellite is already going fast enough and can begin to fall around the Earth. Out at the distance of the moon, where the Earth's gravity is weaker, the necessary speed drops to about 0.6 of a mile per second, which is about 1,000 meters per second. Let's go back to Woolsthorpe one more time. Imagine you are Newton. You've just figured out how the universe works. What do? If you just said, I'd tell someone, or I'd write a book about it, well, you or I might do something like that. Newton didn't. He more or less said to himself, cool, solved that one. What's next? He studied many other things. Some months later, with the plague finally fading out, he went back to Cambridge, eventually became a professor. There he studied optics, mathematics, invented a new and much better telescope based on a big mirror instead of a lens. He studied alchemy, theology, etc., etc. Years went by. Around 15 years later, his friend Edmund Halley stopped by to visit and asked him about some new ideas that were floating around, about how possibly orbits could be explained by some kind of a force between planets and the sun. Newton replied, "Oh, I worked all that out a long time ago." Halley was shocked. No one else had yet made the key leap to see that motion on Earth and motion in the heavens ran by the same universal laws. Woken by the conversation, Newton realized he'd better speak up, or the credit for his ideas would eventually go to others. Newton shut himself off from the world for most of the next year and a half, writing his masterpiece, the Principia Mathematica, a book that would finally explain his ideas to the world. It included the famous 3 laws of motion. First law, the law of inertia. A body at rest tends to stay at rest. A body in motion tends to stay at motion at a constant velocity. Number 2, the law of force and acceleration. F equals ma. And number 3, the law of action and reaction. For every action, there is an equal and opposite reaction, by which he meant all forces are interactions with equal and opposite sides. And of course, it included the law of universal gravitation and showed how this could explain orbital motion, the tides, and many other things. Most of all, Newton made it clear that nature's laws are universal laws. If the Earth pulls the apple, then it pulls on the moon as well. And if that pull makes the apple fall, then it must make the moon fall too. What is true of apples and Earths must also be true of everything. Everything in the universe interacts with everything else, and everything responds to these interactions in the same way, according to the same mathematical laws. The Principia Mathematica was published in 1687. These astoundingly profound and successful ideas became the core of physics and the model of how to use science and math to understand nature. Let 3.5 centuries go by as other people build on this foundation, and the modern world is the result. Amazing what can come from an apple and a little thought. Let's let Sir Isaac himself have the last word. He once wrote, "I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore, and diverting myself in now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before